My name is Daniel Rivas, and I will be presenting large-scale video analytics through object-level consolidation. Edge video analytics refers to the analysis of IoT camera streams happening on edge locations. Edge video analytics is responsible for multiple current and future use cases, such as autonomous driving, traffic management within smart cities, customer analysis in retail, or crop monitoring in agriculture. This analysis is mostly powered by computer vision and deep learning, which are powerful but can also become highly computationally expensive, especially if we consider the limitations present at edge locations. Therefore, we could argue that a centralized cloud is a better option to compute the analysis. However, the main characteristics of IoT cameras used in edge video analytics is the fact that these cameras commonly stream 24/7. This implies that each camera, over time, generates a high and continuous amount of data that must be analyzed somewhere. In addition, many of these use cases have strict latency deadlines. Combined, these two aspects make centralized cloud an unfeasible solution to process all the streams. We have to rely on edge computing. However, a distributed edge cloud infrastructure has limitations concerning the available compute resources. This limits the size and complexity, and also indirectly the accuracy that we can expect from neural networks that can be executed at edge locations. This is especially true when we're aiming at real-time performance. State-of-the-art neural networks often require hardware acceleration, but that is rarely available in the edge, due to power and thermal limitations. For example, consider this figure, which shows the latency in milliseconds and the mean average position of the models that are available at the TensorFlow model zoo. If we set a maximum of 100 milliseconds of latency to execute the inference alone, that is, without considering any round-trip latency or any other pre- or post-processing, we observe how we can expect to run models with 45% mean average precision. Nevertheless, these numbers were obtained using an NVIDIA. Now, let's take this data point here. That corresponds to a faster RCNN network combined with a ResNet 50 classification head. If we wanted to use a CPU for its execution instead of a GPU, the latency would double and be beyond our limit of 100 milliseconds. Furthermore, if we were to use a low-power edge accelerator, such as an Intel Myriad X, we would not be able to execute much more than one inference every second. So that means that as the number of cameras grows, we are facing a scalability problem. And it leads us to the question, can we scale video analytics without also linearly increasing its compute requirements with respect to the number of cameras? For that, we make the following key observation. When considering static cameras, scenes do not move, but objects of interest do. But what is the implication of this observation with respect to edge video analytics? For example, consider the following scene. On the one hand, we have static objects. Those are objects that do not move and will stay there, captured by the camera for as long as the camera is recording. On the other hand, we have moving objects. Those are objects that either enter, leave, or move within the scene. But why is this important? Well, because from the entire scene, the moving objects represent just a small fraction of the total area. We have analyzed images from the different scenes of the Vira dataset. The figure shows the percentage of area that is occupied by objects in each scene of the Vira dataset. These results show two things. One is the world is mostly empty, and objects represent as little as 2% on some of the scenes and no more than a quarter on others. Moreover, some scenes appear to be quiet, which means that only a tiny fraction of objects in the scene are moving. When considering moving objects only, the average area taken by these objects fluctuates between 1 and up to 8% of the area of the scene. What these results highlight is the potential benefits that can be achieved by removing all the empty regions and only considering those regions that are of interest. Consequently, in this paper we propose FOMO, Focus on Moving Objects. That is a method that enables large-scale video analytics by extracting the regions that contain moving objects and filtering the rest of the scene out. Therefore, we can consolidate all the regions from different scenes into a single composed frame that can be processed by a single forward pass of a neural network, that is, a single inference. Moreover, as each scene is broken down into multiple smaller objects, these objects can be distributed and can be treated as the minimum unit of work. Consider 4 cameras at 4 different locations. Each camera captures a scene where the objects come and go. So that means objects are moving. They are either entering, leaving, or moving within the scene. Then we can apply different computer vision techniques to detect those regions where the objects are moving and extract them. Finally, we can merge all the regions belonging to all different cameras into a single frame. In the resulting composite frame, we have removed all the empty regions from the original scenes, and the only thing that's left are those regions where we detected movement, which are those regions that we're interested in identifying their contents. FOMO relies mostly on background subtraction techniques. There are multiple existing techniques for this purpose, but there is no standard method. There are multiple methods, and each one provides a different trade-off with respect to accuracy and performance. The good thing is that many available techniques can be computed on real-time on resource-constrained nodes. This is important as this step has to be computed for every single stream to extract the objects that will make it into the composition. Once objects have been extracted from a scene, have to be allocated into a composite frame. Allocating objects in a frame is an NP-hard problem, and for that we approximate it using a first fit heuristic. A suboptimal solution for this problem generates frames that contain blank spaces. This implies that objects will appear smaller once they are resized to the neural network's input size. However, this does not necessarily translate into a lower accuracy of the models. For the evaluation of FOMO, we have used the BIRAT dataset, which contains 11 scenes from different cameras in different contexts. Moreover, we only consider objects that are moving. The rest are discarded. And we have designed 3 experiments to evaluate the accuracy versus the resource savings, that is the consolidation level, the impact of the background subtraction methods, and finally the composition performance. The goal of the first experiment is to test FOMO's boosting accuracy versus the resource savings we can expect. For that, we test 3 pre-trained models that are an SSD MobileNet V2 with different input sizes and a slightly different architecture. These models are evaluated on 2 different inputs. First, the full frame as captured by the camera, which can be considered the baseline. Second, we test the models using FOMO to consolidate objects that are extracted from the scene using the ground truth annotations provided by the dataset. That means that no objects are missed. Therefore, this method can be seen as an upper bound of what can be expected from FOMO in terms of accuracy. The following figure shows the mean average precision, average for all scenes of the BIRAT dataset, achieved by the 3 pre-trained models evaluated. The baselines, represented as straight lines, use the full frames captured by the camera as inputs. That means that every frame translates to 1 inference. In this case, baselines are 21, 22, and 34% mean average precision for all 3 models. On the contrary, as we increase the number of frames that we compose, we're reducing accordingly the number of inference required by the system. Moreover, we observe how the accuracy increases considerably as we use FOMO to compose frames. The leftmost results represent the case when only objects from a single frame are composed. That means that we're still incurring in 1 inference per frame as the baseline, and therefore not saving any computation. But the resulting accuracy seems to compensate this fact. The accuracy boost is up to 2x for some of the models. As we increase the number of frames to consider during composition, the accuracy drops. Nonetheless, even with 8 frames, which means that we're reducing by 8 the number of inference performed by the system, all 3 models are still well above their baselines. It is important to notice how the model with the larger input size seems to degrade its accuracy slower than the other 2, as the number of cameras increase. The goal of the second experiment is to test the impact that background subtraction methods have on accuracy. For that, we test the same 3 models as in experiment 1, and we test them using 5 different methods for background subtraction. First, the ground truth objects using FOMO for consolidation. That is the same ground truth object extracted from the manual annotations provided by the dataset as in experiment 1. Also, the full frame, which is again the baseline, and then a mixture of Gaussians, pixel to pixel min, and hybrid, which is a mix of the two previous. The following results show the recall, average precision and precision of the 3 object detection models using the 4 background subtraction methods considered, plus the baseline. On the one hand, the results show how FOMO performs compared to the baseline method. The upper bound can again be defined by the ground truth annotations, as no objects are missed during the extraction. This method, the upper bound with ground truth objects, consistently outperforms the baseline by a considerable margin on every metric and model, except on one case, where it lags behind for 10%. Comparing the average precision, ground truth achieves twice as much as the baseline on 2 models and 30% on the larger model. On the other hand, these results show what can be expected by using a more or less accurate background subtraction method. The mixture of Gaussians and the hybrid methods are close on all metrics. Again, precision is where FOMO seems to provide larger benefits, especially for the small input size models. Both MOG and hybrid outperform baseline's precision by a factor of 2 when using the smaller models, and close to 50% for the larger model. Nevertheless, the average precision of both methods still outperforms the baseline by a 60 and 30% when using the 2 smaller methods. Finally, pixel to pixel min, which can be considered the naive approach to background subtraction, lags far behind on the recall and also on average precision. Nevertheless, these results show that FOMO consistently increases the precision, regardless of the background subtraction method used. The goal of the third experiment is to evaluate the compositional latency. That is, the latency corresponding to the allocation of objects on the composite frame using the placement heuristic. This way we can evaluate how an increasing number of objects from different scenes may impact the time to compose a frame. The following figure shows the compositional latency in milliseconds with respect to the number of objects considered during the composition process. We can see how increasing the number of objects leads to an increasing latency. However, most of the data points seem to be under 100 milliseconds in this region. However, there are some points as we increase the number of objects that go past what could be accepted if we are looking for real-time performance, up to 400 milliseconds. However, it is important to notice that looking at the color representing the width of the composite frame after the composition, that these composite frames are too large to be processed by a neural network like the ones we're considering in our evaluations. To conclude the presentation, we have presented FOMO, a method to consolidate video analytic workloads while improving accuracy and resource utilization of the system. On the one hand, we've seen that with 1 inference per frame, which means that no compute is reduced, we achieve 2x accuracy boost. On the other hand, consolidating 8 cameras, so that means 8-fold reduction on the number of inferences, we achieve a 40% accuracy boost. Moreover, we have evaluated different background subtraction methods, and we've seen that FOMO consistently boosts precision by a minimum of 80%, even with the most naive background subtraction method. Finally, we've evaluated the composition latency, and we've seen that it can increase beyond what is needed for real-time performance. For this reason, we're working on adaptive composition policies based on the telemetry and the current load of the system to add more or less objects to the composition. Moreover, we consider that more research is needed in order to predict the impact on accuracy from adding more objects to the composition. This work also opens a new line of research, as now frames can be considered a new type of shared resource that different cameras or different edge locations can use to allocate their work. And with that, I would like to conclude my presentation. Thank you very much.